starting with limits. All right. So first thing that we have to remember about a limit is no matter what, when you are asked to evaluate a limit, first thing that you should do when you are asked to evaluate a limit is always plug it in, always. Okay. Even in the past few years, people in BC have had trouble with this. They'll get some like basic simple limit that looks like it should be evaluated using L'Hopital's rule. So they'll go and use L'Hopital's rule, but they didn't plug in the values and see if it actually was indeterminate. So plug in the values. If you get a number, you get a number, and you're done. Right? Just plug it in. Okay? If you don't, if you get something like 0 over 0 or infinity over infinity, this means you can immediately use L'Hopital's rule, which we know means take the derivative. Oh, that doesn't look like derivative. Take the derivative at the top divided by the derivative of the bottom. Right, if you get 0 over 0, infinity over infinity, you can loop L'Hopital's rule as many times as you might need to, as long as you keep getting an indeterminate form, 0 over 0 or infinity over infinity. Don't try to use L'Hopital's rule for something like 7 over 0. Right? This is not L'Hopital's rule. Don't use it for this, right? Or if it's something like, even every once in a while, I'll see somebody do something like this with L'Hopital's rule. These are not L'Hopital's rule, right? It's got to be 0 over 0, infinity over infinity. If we get something when we plug in our number that we have there, like, suppose we get something like 2 over infinity, we know that that's equal to 0, right? Any constant over a very large number is always going to come out to be 0. If we have our infinity over whatever 3 or something like that, it's going to come out to be infinite. These limits are going to tell us that we have a vertical asymptote at whatever value we are approaching there. And so if our limit comes out to be something like that. Common limit type questions are they like to throw things like these, like absolute value of x minus 2 over x minus 2. And then they'll say, what's the limit as x approaches 2 from the left? And so for these, we have to think about what's happening. If I plug in a number to the left of 2 into this absolute value, something like 1.99999, that makes the thing that's inside of here a negative number, which means that this really becomes the limit as x approaches 2 from the left of the opposite of x minus 2, because we have to remember the definition of the absolute value, right? And so the definition of the absolute value is if the thing inside of it is negative, take the opposite of it. If the thing inside of it is 0 or positive, keep it the same. So since this is approaching from the left, this becomes the opposite of x minus 2 over x minus 2, which is just negative 1. So this is a really common one that they like to throw in the multiple choice. Things like this. They might also, though, do it with the limit as x approaches 2 from the right of the same type of function, which in this case, if I'm approaching 2 from the right, this thing inside the absolute value is positive. So we've just got something like x minus 2 over x minus 2, which just gives us 1. So be careful with those. And they might, and sometimes they'll even just do it with the two-sided limit, right? The limit as x approaches 2 of the absolute value of x minus 2 over x minus 2. And we should know that one doesn't exist because the left and the right hand limits aren't the same. And so the important thing to keep in mind with that also is that the limit as x approaches a of a function equals L if and only if, I'll write this in big letters, if and only if the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, and they're both equal to that same value of L. So the limits from the left and the right have to be the same. If they're not the same, then the two-sided limit doesn't exist. And oftentimes they will throw in something, and they'll give you like a little picture where they're going to do something, like, who knows what they're going to do, but, something like this. And then they'll ask you for, limits at different points here. And they'll be like, all right, let's suppose this is -1. They'll just be like, what's the limit as x approaches -1 of f of x? And we'll say a two-sided limit. You'll say, well, from the left, the limit is 1 but from the right, the limit is 2, and therefore this limit doesn't exist. All right. Everybody good with that? Yeah. They might ask about the limit as we approached 2, right? If we asked about the limit as x approaches 2, well, that one does exist because from the left and from the right, we're approaching the same value. Even if I threw in some extra point up here, just remember that the limit is what we get as we are approaching 2, not what we get when we actually get to 2. So this is the value of the limit where that open circle is. Everybody good so far? All right. If you don't feel like doing L'Hopital's rule for 0 over 0 or infinity over infinity limits, we're going to go back to that real quick. There's lots of other ways to deal with it. Sometimes you might end up in an infinite loop using L'Hopital's rule. So remember, if you have 0 over 0 or infinity over infinity, you can, I would recommend first using L'Hopital's rule. And if you ever use L'Hopital's rule on the AP test in a free response question, you have to write out that you use L'Hopital's rule. You write using L'Hopital's rule, and don't just write LH. Write that you use L'Hopital's rule, like specifically write out the whole statement. Otherwise, they're not going to give you the points for it. So that's first thing. But you can also, sometimes you can factor. It's one way to deal with one of these indeterminate limits. You can also do a U substitution. You can also multiply by the conjugate if you need to, if L'Hopital's rule isn't working out, if it gives you an infinite loop. And oftentimes when you do one of these methods, or oftentimes when you're trying to do L'Hopital's rule, but the limit is infinite or the limit is 0, sometimes you have to go to one of these other methods because L'Hopital's rule ends up going into an infinite loop. So that makes sense. Those are some of the other options that you can use. You can also, that's all I can think of offhand for this. Other indeterminate forms that we've dealt with. We've dealt with lots of other indeterminate forms, right? We did like 0 to the 0. We did 1 to the infinity. What else did we do? We did infinity. Well, we won't do infinity minus infinity here. Man, well, what other? Somebody rattle off some other indeterminate forms that we did that I'm not remembering off the top of my head right now. We did 0 to 0. We did 1 to the infinity. Yeah, infinity minus infinity. So I'll do that one in a minute because that one's different. Yeah, infinity to the 0. Yeah, okay. Yeah, so for these ones, that does not look like a 0, does it? Infinity to the 0. There we go. Yeah, and 0 times infinity. For all of these ones, well, actually, we'll wait on 0 times infinity. We'll stick with these ones. For all of these ones, and this is in that sheet that I gave you guys, remember that in order to evaluate these limits, you need to take the natural log. And so when you take the natural log of it, it turns it into a form that makes it much easier for us to go and use L'Hopital's rule. But you have to take the natural log and then you evaluate it using usually L'Hopital's rule. And then at the end, you have to exponentiate it. Whatever your result is, you have to remember that that's not actually the answer to that limit. That's the answer to the limit of the natural log of the function you're looking at. And so you end up with e to that L value. And so I know I got that one written down in that document that I gave you guys. You guys all remember doing that? Hopefully. You want a practice problem for that? Okay. Sure. Eraser is awfully small. All right. Let's see here. Let's do the limit as x approaches let's just do the limit as x approaches 0 from the right of x to the x. And so obviously that's 0 to the 0, right? 0 to the 0, that's one of our indeterminate forms. So we look at the limit as x approaches 0 from the right of the natural log of x to the x, which is the limit as x approaches 0 from the right of x ln x. And so from there, we see that this now becomes 0 times, and then the natural log of 0 from the right-hand side, this is 0 times negative infinity, which is an indeterminate form. One of our other indeterminate forms, which was the one I was just about to write here and do on this page. So this indeterminate form, 0 times an infinite value, we have to rewrite this limit so that we can do it in terms of L'Hopital's rule, using L'Hopital's rule for it. And so there's multiple different ways to do it. But in this case, I guess it doesn't really matter. We could do it either way. Let's do it this way. Let's write this as natural log of x over 1 over x. Right. Those should be the same thing. Right. Natural log of x times x, or natural log of x divided by 1 over x is equivalent. And so now when we do this, this becomes an infinity, and then 1 over a very, very, very small number is another infinity. So this is an infinity over an infinity, which means we can use L'Hopital's rule. I'm going to write LH, even though you're going to write using L'Hopital's rule. And then you'll take your derivative, which ought to give you the limit as x approaches 0 from the right of 1 over x. And then the derivative of 1 over x is negative 1 over x squared, which ought to be the limit as x approaches 0 from the right. If we flip this all around, this becomes negative x squared over x, which should just become 0. If we cancel out the x over x, we just have negative x, and as we approach 0 from the right of negative x, it's 0. And so then we will remember that what we did originally was we took the natural log, and so we have to exponentiate. It becomes e to the 0. Oops. All seem familiar now? Cool. And that sort of takes care of talking about the form of 0 times infinity. Anytime you get 0 times infinity, you need to rewrite it so that it's 0 over 0 or infinity over infinity. And then you can use L'Hopital's rule for it. So just like trying to deal with x, ln x, which is in fact the one that I was going to do for 0 times infinity. Then the other indeterminate form that we dealt with was infinity minus infinity. And so for these ones, we dealt with these way back at the beginning when we were first talking about L'Hopital's rule. But we also have dealt with them a few times when we've looked at improper integrals, where we had something like, we ended up with like looking at the limit as, it was like the limit is a approaches infinity of like natural log of x minus natural log of x minus, I don't know why I wrote a approaches infinity, x approaches infinity, natural log of x minus natural log of x minus 1. And so this is infinity minus infinity. But what we end up needing to do for something like this is we need to rewrite it. So anytime you have these, and they either come usually in the logarithmic form or they'll come in like a fractional form. So it'd be like 1 over x minus 1 over x minus 1 or something like that. As x goes towards infinity or something like that. Or sorry, as x goes towards 0. And then you'll rewrite it as a singular fraction. So these ones we're going to rewrite as a single logarithm. And then we'll say, well, what happens to the argument of natural log as x goes towards infinity? Well, as x goes towards infinity, x over x minus 1 approaches 1. So this becomes the limit as x approaches infinity of the natural log of 1, which is just 0. And so you just need to combine. Usually they show up in logarithms. Sometimes you might see them in like inverse tangents and stuff like that too. But you just got to combine the two different terms together and then work to evaluate the limit from there. Does that make sense to everybody? Cool. Anybody have any other questions on the basics of limits? We'll talk more about it as we talk about the definition of the derivative, because that's important to touch on briefly, and also when we talk about improper integrals again. But I think that kind of covers the whole limits, everything that we did. Anybody have any limits, questions, or issues that they might have? All right, yeah, intermediate value theorem is not quite limits, but that's fine. We'll talk about it real quick. Oh, and we're going to talk about definition of continuity too. So, in fact, I'll talk about continuity first. There are 3 criteria, because we need this to do intermediate value theorem. 3 criteria for my laptop and my desk at school. 3 criteria for a function to be continuous at a point, and I'm pretty sure I got this in there also. So if I want it to be continuous at a point, we'll call it C. 3 things must be true. Number 1, f of C must exist. And 2, the limit as x approaches C of f of x must exist. And 3, 1 and 2, we'll just say 1 equals 2. Right? F of C must equal the limit as x approaches C of f of x. Right? So those are the criteria for a function to be continuous at a point. Sometimes in the free response, they might ask you to specifically explain why a function is continuous at a specific point. And anytime they do that, anytime they ask you, why is this function continuous at this point, or is this function continuous at the point, they are expecting you to show all 3 criteria are true, that the function exists at the point, that the limit exists at that point, and that the function's value and the limit's value are the same at that point. If you don't do those, then they're not going to give you the points on those. So good. All right. And so then for the IVT, for the intermediate value theorem, the conditions that initially need to be met are that the function has to be continuous on the interval from A to B. And so the function, yeah, I mean, we should be able to tell if a function is continuous on an interval just by what we know about the basic natures of functions. But if you do use intermediate value theorem to justify anything, you need to make sure you state that the function is continuous on that interval from A to B. And so what the intermediate value theorem says is that for any value, so for any, well, let's say we'll write it this way, for any f of C, that is, well, let's write it this way. We'll just say for any y value between f of A and f of B, there must be a value, and we'll call this y value f of C. For any y value f of C between f of A and f of B, there must be a value C on the open interval from A to B, such that well, there must be a value here. We don't need to write anything else to that. So if there's any y value that's between f of A and f of B, there must be a value of C on the interval of A to B that gives us that y value. So if I have a function going from A to B, from A to B, and it does something like this. Doesn't matter exactly what it does, but for every value that is between f of A and f of B, I know I am 100% guaranteed, that if I suppose this is 1 and this is 7, well, if I say, is there a place where the function equals 6 in between? Well, most definitely. There must be a place between A and B where the function equals 6, because this function was continuous, and I could not have possibly skipped over 6 for a continuous function to get from 1 to 7. And oftentimes, this will be used to prove that there is an x-intercept of a function on a specific interval. So that if I start, if f of A is negative and f of B is positive, or vice versa, that if the function is continuous, we know that there must be a place where the function crossed through the x-axis because we went from a positive to a negative value. Is that good for everybody on the IVT? Cool. All right. Next little thing here then with limits is the limit definition of the derivative, right? The limit as h approaches 0 of f of x plus h minus f of x all over h. And sometimes, and we didn't really talk about this one much, but the other formal definition of a derivative should be the limit as x approaches a of f of x minus f of a over x minus a. So two different ways that this can be written, and it's quite often, I mean, this one is I think this one is the one that's more often used, which is why we do it more often in our class. But this one is just as good. And you'll often see multiple choice questions where they'll ask you this limit. They'll say, like, what's the limit as h approaches 0 of something like 3 plus h to the 4th minus 81 over h. Okay, they'll do something like that. And while this is not that difficult to solve using L'Hopital's rule, what they are really hoping that you will do, and what will make your life a little easier than trying to, it's not like it's difficult to differentiate it, but you can use this idea of the limit definition of the derivative and say, well, this is the function f of x equals x to the 4th. I have an x value of 3 plus h to the 4th minus, if my x value is 3 to the 4th is 81, right? And so this is f of x equals x to the 4th. This question is asking you what is f prime of 3, so it's 4 times 3 cubed. And so they'll often do that, and they might do it with either form there. So just be aware of that. And not that you have to recognize this, but it does often make it easier. You can also just say, well, if I plug in 0 for h, this is 81 minus 81, 0 over 0, and you then use L'Hopital's rule, and you end up with 4 times 3 plus h to the 3rd. And then you just plug in your 0, and it's 4 times 3 to the 3rd. You get the same thing. But it might be nice to note that that is the limit definition of the derivative. Good or no? All right. And so we got to think back and remember, what does a derivative do for us? A derivative just tells us what the slope of the tangent line is, or what the slope of the function itself is at a specific x value, right? And I'm not going to go through and like remind you of the power rule, because you don't know how you would have made it this far without knowing what the power rule is. But do remember that if you ever have a product of two functions, especially when you're trying to do like implicit differentiation, like something like x times y, if you're trying to differentiate, that you have to use the product rule, right? Anytime you have a quotient of two functions, you have to use the quotient rule. Anytime you have a composition of two functions, you have to use the chain rule. And it's good to just know, right, if I have a composition of two functions, exactly what the chain rule looks like. So you should know that this is f prime of g of x times g prime of x. This is the chain rule, right? So you want to make sure you know this. That makes life a lot easier because they don't always just give you like the functions themselves. Sometimes they'll give you something like what's the derivative of f of 3x squared, right? And so you need to know that that's f prime of 3x squared times the derivative of 3x squared. So just make sure you're able to use the chain rule for not just like a function, not just a composition of two functions that you can easily see, like sine of 7x, but make sure you can use it in this like standardized form as well. Okay, and we should, I don't think we probably need to go over how to write the equation of a tangent line. Just take your derivative, find the slope, and then use the point and the slope and write it in point slope form. And just remember that you don't ever need to take it out of point slope form unless they specifically ask you to. You're free to leave it in that form if you wish. And I recommend that you leave it and don't try and do the extra algebra, because if you do the extra algebra, it's just a chance to make a stupid mistake. If they ask you for the normal line, right, remember that the normal line is the perpendicular line to the tangent line. So you take the opposite reciprocal of the slope and then use that same point. If we are asked to find, let's see, if we're asked to find the derivative or the slope of the tangent line to a polar function, we're getting the polar stuff a little bit. Suppose I give you r equals, wait, we're just gonna have a nice simple one, right? And we want to find dy dx. Well, dy dx, remember, should be dy d theta over dx d theta. This is still the slope of the tangent line. And so we have to be able to write y equals our r value, theta times sine theta, and our x is theta times cosine theta. And then you'd find the derivative. You'd find dy d theta, you'd find dx d theta, and you'd divide them. And if we have a parametric, suppose I gave you a parametric, we'll just call it x of t, y of t, dy dx should be dy dt over dx dt. Everybody good there? Yeah, there's second derivative of a parametric. So to find the second derivative of a parametric, and you do the same thing with polar, but they're never, I've never seen them ask about the second derivative of a polar function. So the second derivative of a parametric should just be the derivative. So the second derivative with respect to x to find the concavity of it. You need to take the derivative with respect to t of dy dx, which is in terms of t because you've done dy dt over dx dt. So you take the derivative of that, and then you're going to divide it by dx dt. And that's just a matter of the chain rule. I'm not going to go through the whole derivation of that. But the second derivative of a parametric is always the first derivative. You find the first derivative, and you take the derivative of that with respect to t and divide it by dx dt. Okay. And everybody good with that? That good, Darius, or no? Everyone's good. What else? Let's see here. We know when we know how to use our derivatives to do simple things with our functions. So, if we're looking for looking for when the function is increasing or decreasing. The function is increasing if f prime is greater than 0. Function is decreasing if f prime is less than 0. A function is concave up if f double prime is greater than 0.
and a function is concave down if f double prime is less than 0. If f prime changes signs, we've got a local max or min. If f double prime changes signs, we've got a point of inflection. And remember that f prime can change signs both at a place where the derivative is equal to 0 and at a place where the derivative is undefined. Same with a point of inflection. F double prime can change signs at a place where the second derivative is 0 and at a place where the second derivative is undefined. Everybody good with that, I hope, so far? We should also remember that if f prime equals 0 at x equals c, you can look at f double prime of c. If f double prime of c is less than 0, that tells us the function is concave down. It tells us that we have a max. And if f double prime of c is greater than 0, it tells us the function is concave up and we have a min. But this only works if f prime equals 0. It doesn't work when f prime is undefined. And that's the second derivative test. And that can be very convenient, both in the multiple choice and in the free response, because they may just give you like a chart of values. You know, they may give you a chart of values that says something like, you know, here's another row in here. Here's x, here's f prime, and here's f double prime. Right. So suppose that at 1, 2, 3 here are x values, and suppose that f prime is 0, and that's 3, and that's 1, and that's 0, and that's -2, and that's 6, or something. I don't know. And then they might ask you, okay, well, does f of x have a minimum or a maximum at x equals 2? Well, you should be able to say, okay, well, the derivative is 0, so it could be a min or it could be a max, and then my second derivative is positive. Second derivative is positive. That tells me it's concave up, which tells me it's a min. Right? And the same thing here at 3. The first derivative is 0. Second derivative is negative there, so it's concave down, so it's a max. So I like to do that kind of thing in charts to just make sure you know that second derivative test. And obviously, you don't always have to use the second derivative test on just like a regular problem. You can also just make a sign chart to prove that something is a max or a min. Good? Not good? Everyone good? All right. When we talk about intervals of increasing and decreasing, it should always be written using brackets, unless you've got an infinite value. Then you can use a parenthesis for the infinite values. But whenever you do concavity, it should always be done on open intervals. And I don't know why the College Board thinks that for one you should do it with brackets and the other you should do it with parentheses, but that's what they do. So just make sure that you actually do that. But that's the deal with those, right? Good. All right.
Gotcha. Wait, one second. Yep. Quick question. So on the free response, a couple of times, there's those questions where it's like, what's the interval where it's both increasing and concave down? Would you want those in parentheses because it's talking about concavity too?
Yes.
Like with that? Okay.
Yep, 100%. Yep. If they ask for the overlap, it's got to be the open interval. I mean, you know, if you have, so like if you had, I mean, suppose it was increasing from, if they asked when is it increasing and concave up, and it was increasing from 1 to 7, let's say, and let's say it was concave up from, I don't know, 2 to 9, right? Well, then then you would want to say, okay, the overlap of that would be 2 to 7. So then you just gotta be careful with it, because like the 7 is included in the concavity, so you can close that interval off because it's still concave. It's still concave up at 7, right? Because it's still concave up all the way through to 9. Does that make sense?
Yes.
But if the endpoints were the same, then you just use the parenthesis for sure. Cool. All right. Let's see. Let's take a second and think back to parametrics again. So if I give you a parametric and I ask you for the rightmost or the leftmost points, we got to remember that this is just a max or a min of the x. So you're just going to take the x of t value, take its derivative, and look for when it's at a max or a min. And if I ask you for the highest or the lowest point of a parametric, obviously, we're just going to take the y coordinate of it and take the derivative of that and see when it's at a max or a min. Good? All right. Let's see. Related rate problems and optimization problems. Remember, an optimization problem is just, it's just an application of the derivative. It's just find the derivative and see when it's at a max or a min. Hard part is writing the equation. Usually, there's not going to be any optimization in the free response, but there might be in the multiple choice. And generally, they're not too difficult. Generally, they're pretty straightforward to write the equations for those. The same with the related rates. Just remember that when you're setting up your related rates and your optimization problems, there's a lot of good formulas that you want to try and remember to use, or that you just things to look for. Obviously, the Pythagorean theorem is a good one to keep an eye out for. They usually will give you the area or the volume of most fairly irregular shapes. So that if it's a cylinder, they're probably not going to tell you what the area, the surface area, or the volume is. But for like a cone, they probably will. If they do ask you like a rectangular box, they're not going to, but you should be able to figure that out. So make sure you just sort of refresh your memory on those volume formulas just in case. And that they also oftentimes use similar triangles. Right? So make sure you look for similar triangles. All it takes to have two triangles be similar is two angles that match up. So that happens a lot. Like, we had like the street lamp problem with like the kid walking away from it. That's a common one that they like to throw in there. Right? We end up with, they share a right angle and they share this angle right here. And so therefore those two triangles are similar, and you can set up a ratio between similar sides and or similar angles if need be. So just keep an eye out for similar triangles in related rates and optimization. Let's see here. The mean value theorem for derivatives. We should touch on that briefly. Mean value theorem for derivatives. The hypotheses for that are that the function is continuous on the closed interval, and it is differentiable on the open interval. And all it's saying is that if that's true, then f of b minus f of a over b minus a is equal to f prime of c for some c on the open interval from a to b, which is effectively saying that if the function is continuous and differentiable on a closed interval, that no matter what it looks like, it doesn't matter what it looks like, that the average rate of change, the slope between those two endpoints, will at least at one point between those endpoints be equivalent to the instantaneous rate of change, or equal to the derivative. So you may see that in like a chart form. I think we've seen some of those in chart forms during some of our free response practice that we were doing. Or they may just ask you in the multiple choice about. They may just give you a function and say, all right, on the interval between 5 and 10, what do we know that the slope must obtain at least at one point? and then you just find the average rate of change and say, well, the slope, the instantaneous rate of change must be that somewhere. Does that make sense? Okay. Let's see, what else with derivatives and limits? Limits and derivatives. Just remember that now if we have a position equation, the derivative, usually we'll write those as s of t or x of t or maybe y of t. But we'll say x prime of t is your velocity function, right? V prime of t is your acceleration function. Right? Never in the past free response back to 1971 have they ever gone below acceleration to jerk. So you probably don't need to worry about that so much. But just know those, and that the speed is always the absolute value of the velocity. Speed has no direction to it. Speed is always positive. Velocity can be to the right or to the left or up, down. Whereas speed, they don't care about that. So if a problem says to describe the path of the particle, Delphine, what it's asking for is, if they're asking for like the path of a particle that's moving in a line, they just want to know when is it moving to the right, when is it moving to the left, when does it stop. Basically anything you can say about, like if the acceleration is constant, tell them that the acceleration is constant. If it's, basically any information that you can give them, whether it's moving to the right, when it's moving to the right, when it's moving to the left, when it's stopped. Those kinds of things. If you're talking about describing the motion of a particle, we're talking about like vectors, they might want to say whether it's going clockwise or counterclockwise. If it's, suppose moving on like an ellipse or something, say if it's moving clockwise or counterclockwise. Otherwise, they're not going to ask you that about like a specific vector. They're not going to ask you to describe the path of the particle on the AP test. Because usually the function that they give you will be so weird looking, if you were to graph them, there's no good way to describe what they look like. So generally they only ask that if it's just moving in a line, which I would be surprised if they do on the BC test, but it's possible. They usually any one-dimensional, or I guess it's, I don't know, any motion on a line would be in the multiple choice generally on the BC test. And then the other thing important about this is speed is increasing if the velocity and acceleration have the same sign. So that's an important thing to remember. And speed is decreasing if velocity and acceleration have opposite signs at a point. So if and this is something that they may ask you about, and we touched on it once, like 6 months ago or something. Wow, that's a long time ago. That if the velocity and the acceleration have the same sign at a point, speed increases. If they have the opposite signs, speed decreases. So that's a good thing to know. We'll talk more about like distance traveled and displacement when we talk about integrals with all this stuff. We should get to tomorrow. Anything else of like regular limit and derivative stuff that we should touch on that you guys can think of? And tomorrow we'll talk through basically all the integral stuff we did. Just a quick refresher on that, and then perhaps get into series tomorrow. If not, we'll spend all Thursday and Friday rehashing series before we're out of here. Anybody have anything else from derivatives and limits that they want me to talk about? Or that you have questions on? Linear, okay, yeah. So Newton's method, I've never seen a Newton's method question show up on the AP test. So you probably are good there. Linearization, the linearization function is just an approximation. Oh, actually, I should write it. Okay, so the linearization function is the f of a plus f prime of a times x minus a, where hold on one second here. I'll answer your question in a second, Alice. So this is your linearization function. So if I'm looking for, let's say the square root of 15, well, my a value is going to be 16, my f of x is going to be square root of x, and my x is going to be 15. And so this is saying, well, take the value of the function at a number that you know very close to it. So square root of 16 is 4. And then 1 over 2 root 16, the derivative, and then the x value I'm looking for minus a. And so this only works on very small scales. So it's just a good approximation for the value of the square root of 15 by using 16 in this linearization formula. And this linearization formula just comes from point slope form. So this just becomes 4 minus 1/8. And you can get a decimal approximation for that if you want. I mean, it's 3.875, right? But that's linearization. That's about all they'll ask you to do with linearization, is to approximate the value of like a root, or they might ask you to do something like, with a differential, like, if the area, suppose we have the area of a circle, and let's say the radius increases from 7 to 7.01. Well, then they're going to say, well, what's the area changed by? About. Well, it changes by about 2 pi r dr. So it'd be 2 pi times 7 times 0.01. And so they might use it in that way, like a differential also. And as far as Newton's method goes, like I said, they're not going to ask you anything on that, but it's just a matter of knowing what the formula is, and your formula is always going to be, let's see here, your next guess is always equal to the previous guess minus your function over the derivative of your function. So yeah, if you're trying to guess your x-intercept, then you can, you just use that formula and figure it out. So is that good enough for Newton's method for you? And linearization, Nick, or you have more questions on that? Yeah, okay. And then let's see, Alice, what did you say here? You said, should we also know how to do the thing where you find a function with a matrix? Where we found a function with a matrix. I don't remember finding a function with a matrix in this class. Or last school year. I'm going to say no, because there is nothing in Calc BC or AB related to matrices. So you do not need to do anything with the matrix. I don't remember what I did. Was that in AB last year, or was that in quarter 1?
I think you used it this year too. I think it's where you like factor out.
Just where I used a matrix to like solve a system of equations.
I think so.
Yeah, I mean, they're not going to give you a really nasty system of equations. The only place I would envision you maybe seeing a system of equations that you need to solve is within a partial fraction decomposition integral. And I mean, it's not worth their time to like give you a really gross partial fraction decomposition. They're going to give you one. I mean, they're going to give you one in the multiple choice probably, and they might give you one in the free response to just make sure you know how to do it and understand the concept behind it. But they're not going to I mean, they're not really, the point of the whole AP test is not to test your algebra skills, especially not this year or last year. They don't care as much about your algebra skills as they do about your conceptual knowledge of everything. So I wouldn't be too worried about that. Anything else, anybody?